Welcome back. Happy Diwali for all of you. Today's topic is force on current elements. In the last video lecture, we have seen about computing the flux density due to line current elements. And in this video lecture, we will cover the magnetic forces due to current elements. I hope that by the end of this video lecture, you will be able to determine the force on current elements. First of all, let's have a quick recap of what we did in the very first class of unit number 3. We have seen that when a current carrying conductor, let us suppose I'll name it as I dl, which means there is a conductor which is carrying a current, and I'm considering only a small portion of that one, dl. So this particular portion is called as current elements. If it is placed in a magnetic field of flux density B, this is also a vector, then the force experienced by the current element is given by this particular formula. Okay, in this one, these are vectors, and this is the cross product of these two vectors, and the direction of force is perpendicular to both current elements and fields. Okay. Now, let us suppose I'll take a conductor in this fashion, which is allowing a current to pass through it, and let us suppose if it is placed in a magnetic field in this direction. Let us suppose there is a magnetic field and you are taking a current which is flowing in this direction. Now there will be a field which will be developed by in this current element. There will be a force which is experienced by this current element, which will be in perpendicular direction to both the plane of current and also the magnetic fields. This is the direction of force. This is what the vector product indicates. And if you want to determine the force experienced by the entire element, then you need to integrate this particular component over the entire line or the circuit or the path of the current. This is the equation. Let us suppose if you are considering, let us suppose this is a path. Now if you want the force which is experienced by the entire element or the circuit, then you need to integrate this current over this entire path. Now, most of the times we won't be having this particular element in this format, ideal format. So in that case, we will be having surface current elements also and volume current elements also. We have seen line current element is generally represented as IDL, whereas surface current element it is represented as K ds, and volume current element is represented as J dV. This is volume current density, this is surface current density. Okay, so we can employ any of these terms in the place of IDL depending upon our problem data. So if you have been given this particular K value, surface charge element, surface current, then you need to integrate it over the entire surface. If you have been given volume current, then you need to integrate it over the entire volume. Okay. So this is force on the current element, whether it is a surface current element or a volume current element or like linear current elements. These are the equations. Having said this, now let us see if we do have two current elements now. Now this is one current element which is allowing a current of I to pass through it, and this is another element I2. Okay, now I am considering only a small part of this one. See, this particular portion only I am considering. I will take it as I1 dl1, and here also I will consider only a small portion which is I2 dl2. And I'll take that there is a separation of R between these two current elements. Okay, now consider two current elements which are separated by a distance of R, And as per Biot-Savart's law, we know that this current also can develop a magnetic field around it, right? And this current element also will develop a magnetic field around it, isn't it? Now let us suppose this is given by dB1. Since I am considering only a small element, I will take it as dB1. Here also I will take it as dB2. Okay. Now we will consider now this particular current element. Now it is carrying a current of I, and if it is experiencing a field which is created not by its own but by a current which is nearby. So what is the force which is experienced by this particular element? The force experienced by I1 dL1 due to dB2. This is what we are going to study now. Force experienced by one current element due to the field developed by current in nearby elements. This happens regularly in our electrical engineering because most of the times we do have two parallel wires going nearby, and we need to determine what is the force on this conductor due to this conductor. Normally we do assume that they won't have any interaction because they are very far apart, but in practice what happens is there exists a force of attraction or repulsion between them. That is our calculation today. Okay, so now we are focusing on force experienced by this conductor, by this current element due to the field developed in the other one. Now we know that by Biot-Savart's law, the magnetic field is, we have seen B is proportional to IDL and it is inversely proportional to R square, right? So the same I am applying here. So dB2, this is due to the current I2 dL2 mu by 4 pi R square, right? Where R is nothing but the distance. So I have considered this is my I1 dL1, right? And this was my I2 dL2. So I am calculating now the force due to this elements. So the formula is, normally the formula will be like this, right? 4 pi R square into unit vector. Now what I am doing is, my current is this one and I am calculating at this point, and this point distance is R12 or R21. Okay, so B2, this is due to differential element, right? So I'll take it as IDL into UR by 4 pi R12 square. This is what I have written here. Okay, where dL2 is nothing but this direction and UR21 is nothing but in this direction. This is UR21 and this is dL2 vector. So force on any current element we have already seen. dF is equal to IDL into P. Now if this is also a differential element, what this equation will become? du of dF is equal to IDL dV. This is the expression for force on this element due to this field. So I am applying this one now. So force on first element due to field on second element. So d of dF1 is equal to I1 dL1 into dB2. Now, right, we know dB2. What was dB2? This was the equation for dB2, right? And in this one, if you carefully see, I'll remove all the components which are independent. I1, I2 both are independent. Mu is independent. 4 pi is independent. So I am writing them separately. So these are all the vectors. dL1 cross dL2 cross UR2. See, these are all vector products if you carefully see. Okay. Now if I want to integrate it, what I should do? I am having two elements which are to be integrated. So that's why F1 is equal to integral over L1, integral over length of second coil L2 into this entire one. R also will be varying with respect to L, right? So that's why I have taken it inside the integral. This is my final equation. This is the force between two differential current elements. If I want VF2, what I'll get? Everything remains the same. Here what I'll get? I'll get dL2 star, dL1 star, this is what I'll be getting. Okay. This is force on current element 2. Having said this, now we will move on to the practical thing, which is due to very long current carrying wires, right? So we have already seen that the force, let us suppose this is a wire and it is carrying a current I in this fashion. Okay, so automatically how the field will be? See, consider a straight wire carrying a current as shown in the figure. The current produces a field around it, which has been shown with the magnetic lines. See, these are the magnetic lines. They will be in circular fashion, given by your right hand thumb rule or screw rule, whatever you call it. It is given by right hand rule. Okay, so this is the direction. So if this is the current, then this is the magnetic field direction. Okay. Now I'll take now two current carrying wires. See, this is one current carrying wire, this is another current carrying wire. This is carrying a current of I1, this is carrying a current of I2. I'll assume that both are in this direction. Say this is my x direction, this is my z direction, this is my y direction. I'll assume that both are now in z direction. Okay. Now they are placed apart, and see, this is the distance between them. It is the distance between them is d, and the distance, they are separated in x-axis direction. Okay, these are z-axis. If I take this one as z-axis, this is minus z-axis. The current is in minus z-axis mode. Okay, and the separation is in x-axis mode. Okay, and I'll assume that these are infinitely long conductors. We have already done them, right? Let us suppose if there is a current element. I would remind you once again. If there is a current element, what is the field which is developed at this point? Let us suppose that this is H. What is the field? We have already done problems. The formula will be B is equal to mu by 4 pi H into I into cos alpha 1 plus cos alpha 2, right, into U phi. Right, we have already done this one in the last class, and we have already done that if the wire is infinite, then this will become 0, this will become minus 180, and so this particular formula becomes U by I 2 pi H into UL cross UR bar, right? This is what we have done already. This is due to infinitely long conductor. Now we will try to apply the same. Okay. Now the field developed by the current I1 in an infinite long wire at a distance of d meters. So this is the formula, right? For me, I have already shown you in the previous figure that these are the two wires, right? I have taken them as this is z-axis, this is x-axis, and this is y-axis. Both the conductors now are in the direction of minus z. I'll take it as minus k. Okay, so this is UL is in minus k and UD is in x-axis, so I'll take it as I bar. Okay, the force on current carrying conductor I2 due to the field B1 is given by, this is the equation which we have already done, F is equal to IDL into B. Now I am calculating force on this element due to this element. See, what is B1 already? B1 is equal to mu I1 2 pi t into, this is minus k cross I, right? So it will be minus j bar. Now here also, what I'll take I2, dl is in which direction? Yeah. This is dl cross b. Okay. So now I'll take this one as also UL bar. I'll take it as force per unit length. Okay, considering 1 meter length of the conductors, if I take it, this is UL bar, it is also in minus k. So F2 is equal to I2 minus k bar into U I1 2 pi d. This is we have calculated already, minus k star I bar. What was this value? It was minus j, right? So what if you multiply it, what you will be getting? F2 bar is equal to mu I1 I2 by 2 pi d into minus k minus a. What you will be getting? You will be getting minus, right? Am I true? Yeah, it will be minus I bar. So F2 will be mu I1 I2 by 2 pi t. It will be minus I bar, which means the force is being attracted. The force on second element is in opposite direction. See, I have already done this one, right? X, this is Y, this is it, right? So this is the force on this element. How it is? The force is in minus I direction, which means it is being attracted. The second element F2 is being attracted towards first element. Okay. So similarly F1 also you will get what you will get attracted towards your second element. Both the forces have same magnitude but have opposite directions. F2 will be in this fashion, F1 will be in this fashion, which means that they are getting attracted to each other. Now what happens if I reverse the direction in one element? See, I'll take it as B1. Yeah, let us suppose the currents are in this fashion. This is minus K bar and this is K bar, and this is the separation, right? It is in I bar. So what I'll get if I multiply these things? First of all, let me do this thing. B1 is nothing but I'll just only do the vector calculation. So this is the thing, right? So what I'll be getting here? This is mu I1 by 2 pi d, and this is the vector format, right? So what I'll be getting? This is minus j bar, right? So what is F2 now? This is I per unit length I'm considering. So I'll be getting, this is in reverse direction I'm considering now. So I'll take it as K bar cross U I1 2 pi d minus j bar. So what I'll be getting? K bar j is minus I. So I'll be getting plus I bar. So this is mu I1 I2 by 2 pi d plus I bar. This is F2, which means that the force is moving in this direction. The force on this element, due to this element, it is repelling it. So this is what happens if the currents carry in a current in opposite direction. So if both the conductors are parallel to each other, the current is flowing in the same direction, then the forces will be attractive in nature. If the currents are flowing in opposite directions, the forces will be repulsive in nature. Okay. Now, I hope that now you are able to understand the concept of magnetic forces, and I hope that you will be able to compute forces between differential current elements. And this is a simple problem. You need to do the problem and get back to me in the next class. Thank you.